lab safety factor form on the Chem 12B website, so that'll be your lab safety factor grade. I think some of you filled it out already.
Yeah.
I forgot.
I'll
do it now.
I'll do it now.
And then, remember that the take-home portion of the final exam is due this Friday at 8 o'clock.
Oh.
So I'm sorry, 11:30. 11:30. And then the in-class part is going to be this Friday at 11:30. You can only bring one 3" by 5" note card. And like Stephen said, if you want to bring a magnifying glass, you can do that. As long as it's still in a 3 by 5 minutes card.
I got you.
Okay, so let's review for the final exam. Now, before we review, last time we went over reagents, figured out the reaction type, and then we also did a reagent review the lecture before. So let's actually do this. So really, one big part of organic chemistry is figuring out how can you tell how an organic chemical or compound reacts. So in other words, if you're given the reactants and the reaction conditions, how do we figure out what the products are? So all the textbooks say, well, we got to look at the functional group, but really let's look more than that. We want to look at the features of that functional group. So for example, is there an alpha carbon present? Is there an H bonded to a beta carbon? Is there a leaving group, a carbon, carbon, so on? So what I'd like you to do is to fill in these blanks. So for example, is an alpha carbon a nucleophile or electrophile? And in what functional groups do you find an alpha carbon?
Can you say that again?
Oh, it's fill in the blanks.
Are we turning this in? Are we turning those in?
Now what we'll do today is we'll pretend we're under some test-taking conditions, which means you got to work by yourself. And if it's under test-taking conditions, you shouldn't use your book either. Because I don't want you guys getting saying, oh man, I just wish I had my books. I could figure out the answer to this problem. You're not going to have your book. Okay, so for example, does the alpha carbon behave like a nucleophile or electrophile?
Electrophile.
Now, how many different types of alpha carbons are there? There's two. Yeah, because remember that if you have a carbon bonded to a halide, or if you have a carbon bonded to a OH. So that carbon, this carbon here, these are the alpha carbons. Okay, so in other words, you have a carbon bonded to a leaving group, so these two are leaving groups. So that carbon bonded leaving group is an alpha carbon. What's the other type of alpha carbon?
Ketone.
Yeah. So if you have a carbonyl compound, so note that that's also an alpha carbon. So in this case here is the, that's a carbonyl. Here's our carbonyl carbon. So in this case here is the carbonyl carbon a nucleophile or electrophile? It turns out that the H bonded to this alpha carbon is a electrophile, but once that H is removed, then you get, okay, so then you get this one. And then this behaves like a, that's nucleophile. So in this case here, for this alpha carbon, that behaves like a electrophile. So what functional groups do we see this type of alpha carbon? Yeah, alpha halides and alcohols. Anything else? Ketones? Well, see, if it's a ketone, it's not. There's not a leaving group on that carbon to carbon.
Alkynes?
There is a leaving group on an alkyne.
Oh, in functional.
There's a.
Use that acetylide ion to react with alpha carbon.
So you're saying that the acetylide ion there's an alpha carbon there? There's no alpha carbon there.
No, but reacting with the alpha halides.
Are there any other functional groups which have this type of alpha carbon?
Is the CC and the CN one or no?
CC and CN?
Nitro.
Oh, the nitrile? This one? Yeah, because actually the nitrile you can consider, yeah, you consider this to be a leaving group. Yeah, or how about this one?
If it was protonated,
Yep. Yeah, because remember, that's what you do here. So if you protonate the O and the alcohol, that makes this into a good leaving group. Same thing here. So you can protonate the O and the ether. Now that becomes a good leaving group. And then which one's the alpha carbon in the ether? Yeah, ether. Are there any other functional groups that contain that type of alpha carbon?
Files?
Yes, the thiols.
Did we really go into the file reactions?
No, we didn't. But yeah, similarly, these really behave the same way as an alcohol. Only one we covered here is we looked at that skunk smell, which is due to a thioester, or is it thio? I can't remember. Because I actually smelled the skunk smell the other day when I was driving to work and someone had run over a skunk and I had driven past that big skunk and it Nelson. Okay, let's go on to the next one. The H bonded to, no, actually, let's go to this. So here we have a alpha carbon. So what functional groups contain this alpha carbon here?
Aldehyde.
Here we have an aldehyde, a ketone, we have the enolate. So this is our enolate ion. We also have, yeah, carboxylic acids.
And their derivatives.
Yep, all the carboxylic acid derivatives. Okay, let's go to the next one. H bonded to a beta carbon. Okay, so we've gone over one, so now, instead of me talking, since I talked too much, it's your turn to talk.
Leaving groups are almost always nucleophiles, right?
It's an electric.
Yeah, so remember that whenever we look at a leaving group, when we look at Chem 12A, is it is it a strong or weak one? We want a good leaving group.
Strong. Wait. Wait, because it's holding on weak.
Yeah, or a weak base. Weak base.
Which one are we? For carbonyl-carbon, I know that the carbon is the electrophile, but could we still consider the oxygen nucleophile?
Yep.
So as well?
Yeah, because remember in some cases, we wanted to make this carbonyl carbon a better electrophile. One way to do that was to protonate that. Yeah, so really, although this is a nucleophile, the only time we used this as a nucleophile was to be protonated.
Yeah.
Yeah, that was the only time we used it as a nucleophile. Yes, in other words, we don't want to use it, say, in other words, you don't want to do this reaction. So don't say, okay, that's our nucleophile, so that means we can react with RX. So that, we didn't look at the reaction like that.
And or it wouldn't react with another carbonyl-carbon, right?
Right, it won't. Because with the reaction we looked at, it's not this one, we just looked at this one. Okay, so this reaction right now, so it's HCl plus. Okay, so what about the H bonded to a beta carbon? Is that a nucleophile or electrophile? And in what functional group or groups do we find that H bonded to a beta carbon? Yes, that's an electrophile. And we'll find that yeah, so if we have okay, so here's our alpha and here's our beta. Now, did we look at any reaction which involved the H bonded to a beta carbon in a carbonyl compound? Yeah, because we looked at reactions which involved the H bonded to the alpha carbon, but did we look at any reactions in which the H is bonded to the beta carbon for a carbonyl compound? No.
So when we did the alpha, beta, and oxygenated, then we talked about the alpha, beta part and just correct to the position.
Yep. Yeah, so you have the double bond between the alpha and beta. Alpha, beta, and this next. We'll talk about that. Okay, so for the functional groups, which is an H bonded to a beta carbon for reactions that we looked at, we want to look at which. Yeah, alpha halides. So note that in this case here we have, here's our alpha and there's our beta. Yes, the alpha halide is the one. Anything else? The alcohols.
Also, to make the ink, right? The H is 2. And the other one drop.
And that yes, you have a carbonyl compound, like an allyl ketone react with primary amine, and that's going to form. Actually, if you have a secondary amine, that forms an enamine. And is the H, is that from the beta carbon? Because that's the type of elimination. Yes, really, for here, whenever that H is, for the reaction that we looked at, which the H is bonded to the beta carbon, what kind of reaction type? Is that? That's an elimination reaction. Okay, because remember that in that elimination reaction, you needed a base or a nucleophile. So that reacts here, and then what happens? Yeah, so this bond breaks and forms a pi bond, and then this bond breaks and the leaving group leaves. So, you know, after when the semester's over with, think of your big end of the semester party. It was only so easy to get these people at your house to leave your party when the party is supposed to be over with and they just won't leave. That's what you really need to do in elimination. Okay, what about a leaving group? So is a leaving group a nucleophile or electrophile?
Right, you know that how the carbon is C-double-O-R, so,
Yeah.
right, is it single carbon is C-double-carbon?
No. Yeah, it's not a carbonyl carbon, but it behaves the same as a carbonyl carbon. So in other words, if you have this. Yeah, so you're talking about this.
Yeah.
Yeah, so this is an electrophile. That's also electrophile. You get the same type of reactions.
So, the one bonded to it, and then another C on the left side of it,
Yeah, so you have a carbon here.
that's considered alpha carbon for that one? Okay.
Yeah, so whether it's on the left or right, as long as it's one carbon away from that one. So we can put a carbon here, and that's also an alpha carbon too. Should we keep on going? Because I've got a few problems we can do. Let's see, we got one on, so where does it react? Do a few more, so we'll look at cholesterol. We'll look at some amino acids, how they react. Okay, so we'll do these, but this is just to help you make sure when you see these big molecules with all these functional groups, you say, oh, you don't want to panic, say, oh crap, I can't remember anything. I can't remember anything I learned from Chem 12 because I see this big molecule and really all I got to look at is, okay, so these are the function groups here, and then this one here, there's an alpha carbon there, and there's, you know, a beta carbon, and there's this and that. So forget about all the other stuff in there. That's just a distraction. Yeah, that's just, you know, just like when you're working in industry, a lot of the stuff you collect data, but a lot of data you don't use anywhere. Oh, no, we'll just go back. We haven't done, we're not done with this yet. Okay, so you guys done with this? You guys done with this table? You guys figure out whether each feature is a nucleophile or electrophile? I put these dots here because are there more features I didn't put in this table?
Carbocation?
No, carbon, that would be an intermediate, because usually you don't start with the carbocation.
Is it outside of the function? Outside of the function?
It is a set of ether.
It's probably because I have to this is like that.
It should be straight. Since we did the take home, take
No, you did good. That's what you need the tables. That's what you need, those tables, correlation tables, and
yeah.
you need all that stuff. You can't, you're not gonna put that in three. Okay, you got your table figured out?
Share, guys. Share.
For conjugation, what does that mean?
The alternative
Diamonds.
Okay, so does it only apply to dienes? Yeah, benzene. So, for example, does conjugation refer to only pi bonds between carbons only?
No, the carbonyl group and the alpha beta.
Yeah, so that like check is that alpha beta unsaturated ketone is also an example of a conjugated compound. Okay, were there any other features that were not on this table? Okay, so maybe as we go through a few problems, we can figure out more features to put on the table. So let's keep on going then. So just to practice, where does the nucleophile react? Where does the electrophile react with each of these compounds?
There's still a nucleophile.
protonic is a guy and then.
Oh,
But I think reality is
so I was at her desk here.
So electrophile can actually react.
I learned 3 chapters.
But isn't it the oxygen reacting?
Yeah, wait now.
They're both reacting with each other.
So is the nucleophile a lot more because the nucleophile is going to
Possible. I mean, like, well, I mean, that's-
Talking about the X versus OH. Is that what you're saying?
Yes.
But isn't OH stronger nucleophiles than the halides? Or is it dependent on how like iodine is like the most and the bromine is the
I don't know. I've never really reacted with one another.
You have like a hydrogen, you choose which one. Usually it's not one. You have hydrogen and then bromine is the OH is the one. That's like where we're epoxide.
Okay. So where do you react to the nucleophile? You're busting out a lot of things.
Okay, so for example, we have an alcohol here, so where does a nucleophile react with this alcohol?
And the alpha carbon.
Okay, so it could react at the alpha carbon. Any other places you can react? You can also react at the H here. Because remember that the alcohol behaves like as either an acid or a base. Okay, so a nucleophile can react with the H and remove the H and form that alkoxide ion. Or else can a nucleophile react?
The hydrogen bonds with beta.
Yeah, so let's see, we have an alpha, and here's our beta carbon here, so it can react now with the H bond to that beta carbon.
Wait, no,
Wait,
isn't the
you're
other
thinking
one?
of a carboxylic. That's,
Oh, sorry, this one.
yeah.
Or this one.
I was getting confused.
This is,
So was it?
Yes, there's our alpha carbon, there's our 2 beta carbons.
Right. Some kind of heated.
So is this
Now again, before that H can be removed from the beta carbon, you have to do something to this OH group. You gotta put it in, because remember that the OH by itself is a poor leaving group. So we gotta make it a better leaving group. Okay.
Just possible business.
So what about this one? Where does the nucleophile react here?
because there's no
It's an alpha carbon and a beta.
Yeah, the alpha carbon or the H bond to the beta carbons.
So it's substitution or elimination.
Can an electrophile react on the halide?
Electrophile, where on the halide? Here? Nope. 'Cause- Well,
Yeah.
it does. See, we can look at any of the reactions. I can't tell.
It does.
Again, because all of those lone pairs, and lone pairs are nucleophiles. We haven't looked at any reactions in which a nucleophile and a halide react. Actually.
For the reaction you said, for the nucleophile attacking at the alpha hydrogen for the alcohol reaction, how can it attack at the alpha if there's nothing that's a good leaving group?
Yeah, so we have to make this into a better leaving group and put a nucleophile react to.
Oh, so you do that.
Yeah, it's got to be a better. It's got to be. We're going to make the OH a better leaving group before a nucleophile can react at the alpha carbon.
Got it. Okay, thanks.
Okay, so like you said too, these are substitution or elimination reactions. Okay, so where does an electrophile react? Anywhere else?
So the electrophile only does the proton transfer.
The beta carbon.
An electrophile reacts at the beta carbon.
The hydrogen.
It reacts with the hydrogen. No, yeah. Actually, the electrophile reacts with the lone pair on the oxygen.
Right.
And usually the electrophile which reacts at the lone pair on the oxygen is a H, proton, like an acid. It's like you were saying, we got to make this OH into a better leaving group first before we can get a substitution elimination reaction. Are there any other spots where that an electrophile can react with that alcohol?
So does it count on elimination when the proton is reacting with the nucleophile and gives its electrons to the beta carbon to form a pi bond?
Say that again. So you're saying if we have an H bonded to the beta carbon,
Yeah, it's reacting with the nucleophile, and then it gives its electron back to the.
yeah, so that H bonded to the beta carbon is a electrophile which reacts with the nucleophile. Yeah. Are there any other places where an electrophile can react with either the alcohol or the alkyl halide?
So the alpha carbon's reacting with the nucleophile, so that's what counts.
Yeah, those are reacts with nucleophile. We're looking at where does an electrophile react? Is there anywhere else? Okay, so where does an electrophile react with the alkyl halide? Anywhere?
The same.
Yeah, so in other words, can an electrophile react with this compound here? Nope. Okay. Okay, let's keep on going. So let's take a look at some pi bonds. So do the same thing. So let's see, we have a, I'll let you guys can do this. I don't know. What function is supposed to.
And then I love the clay city.
I agree with this, like the last couple chapters.
You want it?
I agree with you.
Oh, yes. I just did. I just in my flow electrons over here, I guess the electrophile can go over to here.
It's like addition reactions.
There's substitution in Oh, I was talking about the other slide.
You're not gonna have questions like from the battle, right? You're just kind of trying to make us think about this. Isn't similar?
Can we go over the final layout? Can we go over the layout?
Where the final? Actually, it's going to be 4 pages rather than 3 because I made sure you have enough room to write structures.
Okay.
There's not going to be a. Remember in exam 1 and 2 we had a problem where there were all like that reaction map. We had to figure either the structure or react. There won't be a problem like
Oh, I
that.
was counting on that.
There won't be a problem like that because rather than doing it all in one, I split it up into several different ones.
So we still should have a reaction map on our.
I think that's good. Yeah, so there won't be problems, there won't be questions similar to this. But this is like you said, Jack, just a reaction, just gets you focused on what to think about if you get stuck on a problem.
So that's the, oh, that we called it, beta, alpha beta unsaturated alpha.
Which one?
The last one, but yeah, beta unsaturated alpha.
Oh, I guess. The hydrogen.
You're not gonna have direct questions on naming, right? But you might just have the chemical formula and we have to figure out like what it is by just looking at like a RCOOH or something.
Yeah.
Okay, so I should get messed up on that.
Names are really hard.
Yeah, I'm not gonna, I won't ask you to specifically name compounds. So I won't give you, say, you know, a list of 5 compounds, say, name this compound.
Would you give us a name of a compound? Experts know what the name is.
Yeah, sulfuric acid.
Or like things like that, not like a
Yeah, they yeah,
So it's easier for me to have like the, anamide or S, so to just see the name and then know what it looks like rather than have the RC like that, because I didn't use it where the bondage should be.
Oh.
It's easier just to have the names of what it is. For me.
Now remember, if you have to, you can ask me for a hint, except it's gonna cost you a half a unit of. Yeah, 'cause you're gonna use, rather than points, it's based on units. Because the in-class course for final exam is only 12 units, or 12% of your overall course rate.
Oh,
Here,
actually.
the take home is 8%, the in-class is 12% of your overall course rate. Okay, you guys done? So for example, where does a nucleophile react with this alkene? So saying a nucleophile can react with the pi bond?
Pybon is a nucleophile.
Yeah, the pi bond is a nucleophile.
So electrophile.
So that means, yeah, an electrophile reacts there. What about here?
Could be.
So we have a conjugated diene here, and does this react with a nucleophile? Nope.
What if you hit a nucleophile to one end and made the pi electrons move?
See, you want to,
During resonance?
Yeah, resonance.
Oh, you created a
oh, so in other words, if you draw a resonance structure, you're saying this actually, if we have
Oh, that's what we
with a
do.
conjugated diene, so if we have this compound,
Yeah, that's when you're adding into our two.
so say you can draw resonance structures like this, and then the resonance structure looks like
With pi electrons on the last.
yeah. So we got to put. Now remember, there's two H's here, so I'm going to put the H's in too.
So if the pybon is reactive, then you have a compound.
Yeah.
But if it's just showing resonance, then you're not going to have a color.
Okay, so what do we need to put on this structure?
A negative charge
On
the far
carbon,
right
carbon 1 or 6.
from the left to the right.
No, yeah, you maybe got a certain number from you. I wouldn't ask you that. You remember from the pi bond. It says carbon 1, so you put a lone pair and minus charge there. Anything else?
Alright, which is the pybon?
Positive charge.
Positive charge on the carbon 4.
Oh, so
Which resonance structure is the major contributor?
That charge is
the neutral one?
Yeah, because when we looked at reactions of conjugated dienes, we really just looked at one reaction, and that was the reaction with
The 1,2 add up and the 1,4 add up?
yeah, the 1,2 versus 1,4.
And what's more stable?
So that was kinetic and thermal?
Yeah, there's that temperature control versus kinetic control versus thermodynamic control. Let's take a look at this one.
That's when you usually.
This is an aldehyde, so where does the nucleophile react with this compound?
Or the beta hydrogen.